Hello, everybody. My voice kind of travels, so if I talk too loud, just please let me know. So, as the paper says, my name is Lawrence Jacob Klinkert. I'm with the Human Game Labs at Southern Methodist University, and today I'm going to go over the procedures and the results from my paper evaluating the efficacies of large language models to emulate realistic human personalities. So, when I started this research about last year, I was trying to look about the problem of how do we improve NPC development and character design to try and represent real human characters. And so there are two fields that I was able to find, either using large language models or using effective computing. And at the time, large language models was only used within the academic sphere. There were some great papers with this, but they always have their own limitations, such as hallucinations, bias, and context length. But another field that I've been looking into is effective computing, which utilizes psychological models to help influence your character design. And typically, this is a very rigid and structured representation, but it can be utilized with a lot of historical backings with psychology. And we can see both in the academic side as well as the industry, it's already utilizing some form of effective computing. And so this was the problem that I kind of focused in on. How do we create believable procedural NPCs and using the bent of looking at large language models and effective computing? So the solution that I came up with this was a procedure to essentially validate the large language models and effectively test them against human data. So how I went about this is essentially giving a large language model a personality test to complete. In particular, I used the IPIP 50 from the International Personality Item Pool, originally having about 1 million records. And the main point that we wanted to focus on was that we wanted to make sure that these synthetic points could have potentially come from the human data. We're not trying to say that the LLM is going to match exactly the human data. We're just trying to see, could it potentially come from that distribution? And so the goals for this framework was ensuring that we had human data as baseline. This was isolated prompting, and we can repeat this test multiple times. And we wanted to ensure that we use metrics that really focused on comparing the synthetic data, comparing the human data against one particular point. And so, as I said, I'm using the IPIP 50, which is a self-reported personality test that determines one's Big Five personality. And you can actually represent this as a 5-tuple structure, where each dimension is represented from 0 to 1. But now using this floating point representation, you get this commented forth problem where it's hard to try and organize this data and ensure where certain personalities are. And so we used a different research that was able to cluster these in 6 different ways, but more importantly, the 12 different personality profiles. And so these spans from both behavioral disorders and their wellness profiles as well. So you have paranoid and pronoid, schizoid, people person, schizotypical, sensible, and so on. And using something like PCA to take that 5-dimensional space, represented in a 2-dimensional representation, we get an idea of what this space kind of looks like. We're going to be coming back to this graph to seeing how the human data and the synthetic data are overlapping with this. So the general pipeline that I used was, as I said, using the IPIP 50, which started out around 1 million test results. And these were all 50 records of the different responses that people had for each item that they used. We needed to be able to ensure that these tests were complete. So we needed data clean this, making sure that all test responses were responded in a timely manner. And we only wanted one submission, so a single IP address. Then we used the provided IP score key that was given to then get the 5 dimensions. And then finally, we did a profile assignment where we effectively do nearest neighbor. So whatever that particular test was, whatever the closest of the 20 profiles were, we assigned that to that particular profile. And then finally, once we had all of these labeled, we wanted to then use a disproportionate sampling to make sure that every profile was represented equally. However, we want to try and keep that distribution of the human data. Then for generating the synthetic data, we were able to select from either a frontier model or a local model. Frontier model being that it's about over 100 billion parameters, and local models being underneath that. Then when we were able to test the responses, we were able to we were able to provide a particular personality profile, specifically the 5-tuple structure, not the name of the profile. We were able to randomize each of the 50 questions and make sure to isolate it. So we're not using the chat history or able to look at previous questions and see how it answered those questions. Then we run it 64 times so that we had a suitable population size and use the same IP scoring and the profile assignment. And in the end, you get something like this. This is a subset of the data that we have, but this shows visually what we're trying to look for. And so what you're looking at with each green cluster representing the human data and the red X to represent the center of the profile location, and each row represents a different personality profile, and each column represents a different LLM model that we tested. And as you can see, going from left to right, it's a different generation, adding more parameters to the model. And you can see that the synthetic data are slowly moving over to being on top of the human data to then now overlapping with the actual profile location. So again, as I said, this visually represents what we're looking for, but now we need to quantify this. And so the first metric that we use is agreement. What we get in is what we get out. We're using K nearest neighbors. We wanted to ensure that the synthetic point, based upon its human neighbors, which of the profiles it was closest to. And using looking at GPT-4, we see that it had a 74% agreement with all of the 20 profiles, within GPT 3.5 coming in second and dropping down significantly down to 32%. And the next metric that we consider is a convex hull accuracy. So given the human data, we wanted to wrap some sort of object around it in 5-dimensional space, thus the convex hull. And then we asked the synthetic point, are you inside this convex hull or are you outside of it? And if it's an inside, it's a potential that it could have come from that human distribution. Otherwise, it's considered an outlier. And as you can see with the breakdown with this web graph, you can see that GPT-4 is showing pretty well with borderline, avoidant, dependent, and so on. And then once again, GPT 3.5 just right behind it. The next metric that we considered is the mean square prediction error, because as I said in the prompt, we said specifically you need to be this 5-tuple structure. So looking at each dimension, seeing how off the error is. This graph is the inverse from the previous one, so we want the smallest circle to represent. Once again, GPT-4 is doing pretty well, having roughly underneath 10% of error, and then GPT 3.5 just right behind it. The next measurement that we considered was the Mahalanobis distance, and this is kind of akin to Euclidean distance, but instead, Mahalanobis distance takes into consideration the covariance of the population. So what do I mean by that? Think of adding weights to each of the dimensions, and if we're allowed to travel vertically in this distribution, then that means there's a lower weight on the vertical sense. But if we're restricted on moving horizontally, then that means there's a higher weight. So we're further away from the actual human distribution. And so once again, GPT-4 is doing pretty well with this. But even further than that, this is also akin to standard deviation. You can actually apply something like the 95 percentile to get a cutoff on where those outliers are. And so with this particular representation, that cutoff would be around 3.3 repeating. And with GPT's result, each one of those are underneath that threshold where GPT 3.5 is already crossing that. And so with that being said, we noticed that GPT-4 was going to be a great candidate for our particular use case. And this game, Dark Shadows, was actually created from a separate initiative called Pangea. I'll be going over this particular project in tomorrow's poster session, but to give it a general idea, it is a Unity plugin where it helps game developers to create JSON files that are specifically defining the game rules and the game scenes and content that they wish to provide. Then the program is allowed to create these procedural mysteries for that particular setup. And so what we're wanting to focus on specifically is actually the interrogation scene on when you're communicating with the NPCs. We utilize my validation process in this, and we were testing it with GPT-4. And for this particular investigation, we're asking this individual who has an obsessive compulsive personality where they were when Lady Eleanor disappeared. And so you can see it has something like make sure that everything was perfect, organize my notes, everything must be in its place. When you change that personality and rerun the same exact scenario and ask them the same question, it's slightly different. Spend some time chatting with other staff. We often gathered by the kitchen entrance for a bit of socializing. And then once again, changing it with laissez-faire, taking it easy after a long day of work, taking a nap. I wandered around the grounds for a bit. And so you can see how utilizing something like this, you can generate the discourse of what you're expecting with the personality that you assign. However, this is where I need to now talk about the limitations of this work. So first and foremost is computational and financial resources. We want to try and test a diverse set of LLMs, whether that be from Hugging Face or GPT-4All, and trying to use as limited as possible to the services, whether that be OpenAI or AWS services. The next one is the assessment tool. As I said, I've used the IP-50, which is a self-evaluated Likert test. And so this was easy for us to utilize because we can scale this. However, if we want to really utilize the LLM, we could consider an interview process where we ask the GPT model how it believes and what are some examples. However, now we need to find a way to take that qualitative data and turn it into quantitative data that we can then scale. Then the other limitation we can talk about is the static prompting. As I said, we asked the GPT model only once the particular question and what they responded with, reset the whole thing and continue with the rest of the testing. The next thing we want to consider is what happens when you start chaining these prompts together. Does it still represent that same personality from time 0 all the way to time 20 and further on? And so in conclusion, we were able to create a validation process that was able to test LLM generated content for NPCs and be able to test that against human baseline data. This procedure is very scalable as long as you have the human data to test against. And then we were able to confirm that the frontier models, such as GPT-4, are already able to represent 100% of the personality for some of these profiles off the shelf. And so there's no fine-tuning already needed. And then future directions that we'd like to look at is exploring other psychometric variables, whether that be emotions, relationships, or other personality models like Myers-Briggs or even D&D stats. We want to extend the interaction testing, as I said, to make sure that the representation of that personality starts from time 0 all the way forward. And then we want to look at other downstream tasks, whether that be a reliability metric or a validity metric. And that's everything that I have. If you have any questions, I'd love to talk about it.